In this video, we're going to do an overview of the material covered in Chapter 7. And Chapter 7 goes through different physical states of matter, gases, liquids, and solids, and then also provides some context for how these different phases of matter transition into one another, while discussing the behaviors that we see for them through the lens of intermolecular forces. So I'm actually going to start with intermolecular forces and then go through our different types of phases of matter. So intermolecular forces are the attractions between molecules rather than the attractions of atoms within a molecule that form bonds. So these are not bonds. But it's still going to be um, like while these are attractions between molecules, it's still a plus minus attraction, right? So it's attraction between a positive and a negative charge. So partial negative charges on one molecule and partial positive charges on another. And so it's still based on that opposites attract kind of rule of nature. And again, as we said, these are not bonds. We won't refer to them as that. And so we have a few of these that exist, and I'm going to show them in increasing order of how strong they are. So we have London dispersion forces. We have dipole interactions. And we have the worst named one, hydrogen bonding interactions. And again, I'm saying the words bonding, but it's not really bonding. And so we see that we increase this strength as we go from London dispersion to dipole-dipole to hydrogen bonding. Our London dispersion forces are going to exist whenever we have an electron cloud. And so that's going to be practically everything. And these are going to be our weakest ones, and they're these spontaneous, temporary dipole moments that exist as you bring two clouds of electrons, which are the same charge, close together. You're going to have one kind of shift. They're going to shift their electrons around, so that way there's a partial positive and a partial negative charge that can come up to one another. Uh, the analogy I use to remember this is that it's like being on a crowded bus, at like a really crowded bus, and you're trying not to touch anyone. This analogy is even more relevant when you think about coronavirus, and you're trying really hard to stay away from everyone. So imagine trying to stay 6 feet away from everyone on a bus. You'd be leaning as someone got close to you, and you'd lean the other way as someone got close to you. And that's what the electrons are doing as electron clouds come near them. They're like, I just got to get away. And it's because those negative charges are going to repel each other, where positive and negative attract. And so something coming close to a molecule coming close to another one will have an attractive force to the nuclei, but a repulsive force to the electrons. Dipole-dipole interactions are only going to occur between molecules that are polar. And these are going to have those permanent dipole moments that we learned about when we talked about covalent bonding. And they'll line up. So the more positive side of a molecule will interact with the negative side of another molecule. And because these are interactions that are permanent and not temporary, it's a stronger interaction. And within that, we also have a subset of dipole-dipole interactions that are just stronger than all the other ones. And we call those ones hydrogen bonding interactions. And it's because they take place between molecules that have a hydrogen atom bonded to either a nitrogen, an oxygen, or a fluorine. And what happens in this case is you get a hydrogen that has a very partial positive charge. And then on the lone pair on any of these, you have a partial negative charge. And it's a larger magnitude of partial charge. So that means an interaction with another polar molecule or another lone pair will be a stronger interaction than a typical dipole moment. And so those hydrogen bonds, you have to have a hydrogen bond within the molecule, and then it will interact with another by forming that interaction between the hydrogen and then let's say a lone pair on another atom of another molecule. And so we're going to be able to use these intermolecular forces to understand some of our behavior of our different phases. Um, and and so when we think about these, we're talking about these attractions that are coming from these positive and negative charges being attracted to each other. And so the strength of that really depends on how close the charges are together. Um, Kind of like if you're holding two oppositely charged magnets, if they're really far away, you don't feel much of a pull, but as you bring them closer, they come together. And so looking at our three different phases of matter, solids, liquids, and gases, we can say that these particles will have more or less space between them. And this is kind of just part of our definition of these. So a solid will have our particles, sorry, stationary to one another. So they'll be in the same place. And their movement will just be vibration, but they'll be in the same spot relative to one another, and they'll be very close together. And this means for solids, we're going to see that their volume stays the same, their shape as well will all be static. A liquid, those particles are going to be moving a lot more. So these ones are still close together, but they're moving. So its shape is changing. And for our gas particles, these are very far apart. And gas particles of very low density. So these are far apart, these particles, and they're moving so fast that both their volume and their shape can change overall for the entire sample. And so the difference really between how close these are together and is comes down to how much they're moving. And so for this solid, it's going to be lower kinetic energy. I'll put it here. For this liquid, we're talking about something that's kind of in the middle. So like the kinetic energy is less than a gas, but it's greater than a solid. And for our gas particles, we'll have high kinetic energy. And when I say kinetic energy, I'm just talking about motion, like the translational motion of a particle moving from spot A to B, or the motion of vibrating or rotating around in space. And so if our intermolecular forces depend on molecules coming close to one another, we can say that in our gases where we have high kinetic energy and our particles are far apart from one another, we can say that our intermolecular forces have very little effect on gas particles. But on our liquid and solid particles where they're close together, we can say that it has a large effect on their behavior. And so intermolecular forces will really dictate the physical properties of our solids and liquids, while our gases will basically ignore them. All right, so now that we have kind of an idea of just like the difference between a gas, a solid, and a liquid, let's talk about properties a little bit more. So we're not going to focus a lot on solid properties. Instead, I believe like the chapter introduces them as crystalline or amorphous solids, and we'll leave it at that, spending more time on liquids and gases instead, which I think will have a larger impact on what we'll learn later in the class and also generally what you'll interact with out in the world. So again, the only distinction here is amorphous versus crystalline. And this just means a crystalline compound has more order to how the atoms are arranged relative to each other. They're just more uniform, where an amorphous solid is a lot more chaotic in how the molecules or the atoms are arranged relative to each other. So then for a liquid, where these particles are kind of tumbling all over each other. As they move around one another, they're close together, so there are intermolecular forces between them, but those forces are constantly breaking as they move past each other and then reforming with another molecule. And so they're constantly breaking and reforming, and they'll have a big impact on the physical properties of liquids. Here. And we see kind of two categories of this. We see physical properties that the effect as we increase intermolecular forces, and I'm going to give my abbreviation here. We usually abbreviate intermolecular forces IMF because it's a really long word to write out. So as we increase our intermolecular forces, we see an increase in physical properties, their value. And then we also have a version where as we increase the intermolecular force, we'll see a decrease in the property. And so let's start with the more straightforward one, that I'm going to increase the strength of the intermolecular forces and the number of them, and see a change in properties because of that. So as we increase those forces, we'll see boiling point increase. Let's write this out. And melting point. And this is just the temperature that these boil or melt, so they undergo a phase change. And that as the strength of those intermolecular forces increase as you look at different compounds, those boiling and melting points, which are characteristic for the compound, will be higher if there's more intermolecular forces. We see viscosity increase as well, which is really how slow a liquid moves across a surface. And that slowness is coming from having to break intermolecular forces to spread out and move. And so if those intermolecular forces are very strong, it takes a lot more energy to do that. And so the liquid will move slower. Surface tension. And our surface tension, as those intermolecular forces increase, it's harder to break those forces. And so if something's going to step on the surface of the liquid and step through it's going to need to break intermolecular forces. And so if the force applied isn't strong enough to break those intermolecular forces, then the object can sit on top of the water like a water skater bug. And if we have higher intermolecular forces, that means it can withstand more force upon it. Now, the one that I'll point out that has kind of an opposite property here, where as we increase the intermolecular forces and they get stronger, we see it decrease, is vapor pressure. Vapor pressure is just the amount of a liquid that actually has enough kinetic energy to be in the gas phase above the surface of the liquid. And so as we increase our intermolecular forces, it takes more energy to convert that liquid particle into a gas particle. And so fewer of those particles can do that. And so we see the overall pressure of the gas above the surface of the liquid decrease as we make it harder to break those intermolecular forces. Now turning our attention to gas, where intermolecular forces aren't going to play a role at all, or we're going to assume they don't. We're going to just then focus on the behavior of gases. And because there's very little effect from intermolecular forces, it means, and this is super cool, that all gases behave the same, despite any chemical differences between them. So we can predict gas behavior and properties just based on a few variables rather than the chemical identity of the gas. And the variables we're going to look at are pressure, volume, temperature, and the amount of the gas that we have in terms of moles, which is N. And so we can relate these variables to one another using the ideal gas law. It's PV equals nRT, where R is the universal gas constant. And there's a couple versions of this that depend on your units. The one I tend to use the most is 0.0821 liters times atmospheres divided by mole Kelvin. And I'm going to highlight that what I just wrote here is not an equation. These are units. the equation itself is the PV equals nRT. The units on our ideal gas law, our gas constant, are there to make sure that the units cancel out properly in the equation so we can actually calculate any of these variables from the other three. So I'd like you to be comfortable with the ideal gas law, which is derived from a number of the individual gas laws. We'll then also look at Dalton's law of partial pressures. Which is really just saying that if we have a number of gases combined and mixed together, that their pressures will add and the number of moles will add. And so we can determine the pressure of just one component of a mixture of gases if we just know the amount that we have relative to the rest of the gases. And this is often written as the total pressures equal to just the sum of the pressures of the individual gases. And I think those are the two laws I would focus on the most. We have a few other things that are in here that are helpful, like this idea of standard temperature and pressure. Standard temperature and pressure will be at a pressure of 1 atmosphere and a temperature of 273 Kelvin or 0 degrees Celsius. Took me a minute to remember. And under the standard conditions, we'll always see that 1 mole of gas will occupy 22.4 liters of volume, like, no matter what the gas is, which is really cool. Within this too, we do have some conversion factors to be comfortable with and aware of. Pressure has just a ton of different units, particularly. So we like being comfortable with PSI and torr and millimeters of mercury. The one that I'll use the most is atmospheres, because that's the one we typically use in chemistry labs. It's what I'm the most comfortable with, and it's a chemistry class. But like my pressure tire is like PSI, and some thermometers, or not thermometers, different pieces of equipment that you'll see in labs or possibly in hospitals will be millimeters of mercury. Atmospheric pressure is usually measured in bar or millibar. Looking at all of these, now I want to kind of tie liquid, solid, and gas phases together, kind of the last piece of chapter 7, which is phase changes. And so this is really looking at these changes between these three states, between a solid becoming a liquid, becoming a gas, or the other way around. And these phase changes are endothermic or exothermic, depending on if you need to increase the kinetic energy or not. And so, thinking about endothermic, this is when we need to absorb energy. And so that's when we're going to make a transition from a phase that has lower kinetic energy to higher kinetic energy, less motion to more motion. And so that's when we're going to go from a solid to a liquid to a gas. And these transitions, these phase changes, are called melting and then evaporation or vaporization. And while I usually probably think about evaporation more, vaporization sounds cooler. And then we also have exothermic, which is where we're really releasing energy. And this is when our phase change is taking particles that are at higher kinetic energy or energy of motion and becoming less, or having less motion. And so they kind of have to release some of that extra energy. And so this is going to be when you go from a gas to a liquid to a solid. And then these transitions are called condensation, if you go from a gas to a liquid, and freezing. And we can characterize these phase changes with heating and cooling curves. And so a heating curve might look something like this. So we'll have temperature over here, and then we'll have just energy that we're inputting. And so we start at a low temperature, and it increases until we hit a phase change. It'll look like this. And our phase changes here are where the temperature stays constant. And so this is going to be our solid becoming a liquid and our liquid becoming a gas. When we hit a phase change, all of the energy that's being inputted into the system is going to go towards transitioning those molecules into the next phase. So like from a solid to a liquid, which means breaking intermolecular forces. And so at low temperatures, you'll have a solid, medium temperatures liquid, high temperatures a gas. And you'll notice that in these phases right here, where it's just one type of phase, as you input energy, the temperature increases. And a cooling curve is going to look just like the opposite, where here's our temperature, and here, instead of inputting energy, we're removing energy or heat. And so we start as a gas at high temperatures, form a liquid and then a solid. And at our phase changes, we're going from a gas to a liquid. And we know we're at a phase change because the temperature doesn't change, it stays constant. And when that happens again, it's when we're converting liquids to solids and freezing. Now, within these heating and cooling curves, we're not actually going to do too many calculations with them, but for phase changes in general, or for these different types of phases, there is something that we can track, which is how heat flows in and out of a system. And so when we do that, we're looking at Q, and that's really our variable for heat. And for any sort of substance, that heat is equal to the mass times the specific heat, which is a physical property of a compound, times the change in temperature. So that's mass in grams, specific heat, which will usually be in joules or kilojoules per mole, per gram, Kelvin or gram degrees Celsius, and then change in temperature, which will be in degrees Celsius or Kelvin. And this equation right here allows us to basically calculate the amount of energy that's needed to increase or decrease to increase the temperature of a substance, or the amount of energy that's released as it decreases. And so you see this occur in these parts of the heating and cooling curve where we have a temperature change. And so if I'm heating a gas from 25 degrees to 50 degrees, I could use this to calculate how much energy it would take to actually do that. All right, and that in a nutshell is chapter 7.